Who has started recording? Hello, am I audible?
Yes, sir.
Okay, good.
Yes, sir.
Okay, so very less attendance. What happened?
There might be programs about Janmashtami festival today evening.
That is good. Anyway, so next week will be the exam. Okay, I hope you know the date. It is already shared with you in the very first class.
Sir, what will be the syllabus of the test?
Syllabus will be most probably up to coming Monday, whatever we will cover. Okay. Okay, so let us share the screen and start the lecture. So, any query regarding the estimation part that we have talked in the last lecture and testing that I have left as a recorded lecture? Any query? Because subsequently we will be using testing a lot. So we were talking about the maximum likelihood estimate and for estimation part, and testing part, I think almost everything I have covered in that lecture of Friday that I have shared. So any query? Okay, if not, then very good. I will assume that you have understand everything of testing and estimation that so far we have discussed. So we have talked, well, the
Sir,
screen.
apart from those like PDF, those notes, I mean, for estimation testing, you were using some another, I mean, slides also in the recorded lecture.
Oh,
Have you
that is,
shared that one?
no, that I have not shared, but that is only 3 slides I have used.
Okay,
We
yes.
just take a screenshot, and that is nothing. I mean, whatever, only the data example was there. What was new? Otherwise, the rest of the thing was just the same thing, copied and pasted from this slide itself, almost.
Okay, sir.
Okay. I have to set the timeout. Okay.
So one thing, you used the notation tau somewhere.
Yeah.
So what was that notation for?
Okay, so for usually when we say normal distribution, say normal 0, 1, then any value is usually denoted by z. Okay, so if I write z alpha, upper alpha value, then usually it is meant by this area is alpha. So probability, let's say capital Z following normal 0, 1, probability Z greater than Z alpha is alpha. This is the usual notion used in for testing or upper alpha value to denote. Similarly, if it is a T distribution, say k degrees of freedom. So if it is tau alpha k, then this region is again alpha. Probability Tk is greater than tau alpha k. This probability is alpha. Is it okay?
Yes, sir. Okay.
So usually this is the notation, and they are known as the upper alpha value. But remember the thing that T and normal 0, 1, they are symmetric, but F distribution is not symmetric. So Z alpha, the magnitude of Z alpha is same as minus of Z alpha. Sorry, Z of, I should say in this way, 1 minus alpha. Z1 minus alpha. They have the same magnitude because Z1 minus alpha is this, and that quantity is same as minus of Z alpha because of symmetry, and same thing will happen here. But that will not hold for T distribution. Sorry, F distribution. So okay, let us talk about the maximum likelihood estimate little bit more in details.
So,
Yes.
so the pattern of test will be MCQ, right?
No. It will be fill in the blanks numerical question. You have to calculate and you have to give the right answer in decimal, and within 0.005 error range. If the answer is, you will get the correct full credit, otherwise 0.
So number of
Okay,
questions
sir.
and time.
It will be 1 hour 1 hour test. I think 50 minutes time you will get, 10 questions will be there.
So can you upload some practice questions or tell us the reference? Because
Reference, I told you that only the book.
so for questions.
Yes, the book's example you follow, that will be given correctly.
So will be the toggling among the questions be allowed? Like we can do the last one and then we can come back to the earlier questions.
No. Only you answer the one question, then only you will get the another question.
So there are so many references. Which book in particular for questions we can?
For questions you can, so far, well, almost everything is under revision. So you can see some part of Montgomery, some from, what should I say, that Buffett. The question will be conceptual because so far we have not entered detail in the regression. So it will be based on the definitions and concepts only.
Okay, sir.
If you,
Thank you, sir.
it will not be say derive this, not like that. If you have understand the definitions properly, you will get it quickly. And more precisely, if you have studied probability statistics very well, it will be much more easier. So it is very much important that probability is very much clear to all of you. And rest of the thing, based on the definitions, only you will be able to answer. Okay. So maximum likelihood estimation that we were talking about in the previous lecture. So let us assume that for simplicity that x1, x2, xn are following. So xn are following binomial, say 10p. This is known. Let us assume this is known, 10p. So n observation are there for binomial 10p. So you are interested to estimate the value of p given these numbers. So here you can see that p can belong to 0 to 1. Okay, and x size can take value between 1 to up to 10. Okay, so the joint density is product over f of xi. So I running from 1 to n. So it is 10 choose xi p to the power xi 1 minus p to the power n minus xi, product over I running from 1 to n. Right. So this is the joint density. Now suppose that the numerical values are known. Okay. So when the numerical values are known, you can plug in the numerical values for each of the xi's. So the likelihood function. So this is a likelihood function is say LP, which is also of the same function, but P is assumed to be unknown here, or P is the variable of this function. Sorry, this will be 10 minus x. So it can be written also as a product of 10 choose xi, I running from 1 to no, n, this is n, and then this is one part, and then p to the power sum over xi, I running from 1 to n, 1 minus p to the power n into 10 minus sum over x. So LP, now you can take the log. So that will make it simple. Log E of this quantity first, product over I running from 1 to n 10 choose xi. So note that this quantity doesn't involve P. Then you have sum over xi I running from 1 to n into log P plus this quantity n into 10 minus sum over xi I running from 1 to n log of 1 minus p. Okay. Now it is trivial. Del LP del P equals to 0, and you let me know what will be the value of P hat. Solve this equation and tell me what will be the value of P. This quantity is free from P. Here is P. Here is P. What will be the value of p hat? Solve the equation and tell me. So what happened? What will be the value of p hat? So this is the maximum likelihood estimate. Is it so difficult to solve this equation?
So summation xi by 10n.
Yes, correct. Summation xi by 10. So this is the solution of, and here you have an example, something similar that we have done. So 10 observations are taken from binomial, 50.7. So 50 observations are taken. 10 observations are taken from binomial 50.7. No, I think x is gone. No, well, no. Here n is written 10. No, so 50 observations are taken from binomial 10, 7. So now, based on this 50 observation, if you just plot the likelihood function, it will look like this. And if you plot the for which value of p it is attaining maximum, it can give you 0.72. So you can see that already the true value was 0.7, and based on 50 observation, if you estimate it, you get 0.72. So if you take another sample, you will get some another number. So in this way, it will be fluctuating always. And if you take the log likelihood, then the log likelihood again will look like this, and it will also attain the maximum at the same place. So as the log already we have discussed, it is 1 to 1 and increasing function over the positive part of real axis, it will be giving you the same value. But you have just seen that the advantage of using log, it often helps us because if you consider this part, it will don't have any contribution in the after the taking differentiation, taking log. So that is. But now you have few properties of MLE, that MLE did not be unique. First of all, if you try this example, you will be able to see that MLE is not unique. MLE need not be an unbiased estimator. So for that, you can also do one exercise. Maybe I have given here. No. Yeah. Okay. So MLE of sigma square for normal distribution, if you calculate the MLE of sigma square, it will be 1 upon n sum over xi minus x bar whole square, and hence it will not be an unbiased estimator. Okay. And few other properties, But MLE is always a consistent estimator. That means as n goes to infinity, MLE will go to the true value with probability 1. So MLE is always a consistent estimator. MLE is asymptotically normally distributed up to certain location and scale change and under some regularity condition. So if you have little bit adjustment with the moment condition and like that, then you will have the MLE is following normal distribution. And the range of random variable, okay, so like this kind of conditions you need that the range of random variable must be free from the parameter. So all of the random variables so far you have seen, they except uniform. When you say uniform AB, then the range of the random variable where the distribution is supported, it is always dependent on the value of the parameter. So those, except those kind of situations, you will get that the MLE is well behaving and the normality property will hold. And likelihood is smoothly differentiable up to third order. This is also an important aspect for having that normality. Okay, so these are all about MLE. So now I think we can move for interval estimation. So instead, already you have seen, yes.
Sir,
Yes.
can you please explain the fourth property of the MLE, like that asymptotically normal distribution?
Asymptotically normal distribution means that if you do some adjustment, say for example, here, this is your p hat, right? So if you study the distribution of this p hat, then p hat minus the true value of p divided by p hat into 1 minus p hat, this kind of thing will be asymptotically following normal 0, 1. Although p is a probability which is lying between 0 and 1, if you subtract its true mean minus, if you use p and 1 minus p, then also it will hold with less number of observation. But if you use p hat into 1 minus p hat, then also it will go to normal distribution as n goes to infinity. So this kind of thing is, this is for the standardization. And if you go for the variance, I think, let me just check, expectation of p hat is p trivially, variance of p hat is 10 times for each of them 10 p into 1 minus p into n divided by n 10 square. So variance of p hat is this. So p hat minus p divided by, okay, so I need to multiply by this quantity, n 10 square root of that. So this quantity will follow normal distribution. So this kind of adjustment you need to do, then only you will be having normal distribution as n goes to infinity. So often it is useful because, say for example, you are testing for this kind of hypothesis. Say it is an unbiased coin. So you need to write the 0.5 here. Here you need to write the estimated values, and then you can go for the testing. But if your sample size is small, then you cannot do this approximation. When your sample size is large enough means it also depends on the value of p. People often do the mistake that, well, more than 35 observation or 40 observation, they are following normal distribution. That is not always correct. If if you see the CLT, I hope in any of your section wherever you were, you studied CLT. If, say for example, if you have data from binomial distribution for p is equal to 0.5, it will very easily converge to normal distribution. But if the value of p is 0.01 or 0.09 or 0.095, then converging to normal distribution will take more number of observation to hold the CLT. So it is ultimately the end product of CLT, but that helps us to have an asymptotic test. Otherwise, you have to have an exact test, and when you have to go by exact test, then either you need to go by the Neyman-Pearson lemma, where you may need to do the randomization, or you need to simulate from the null distribution, and then you need to calculate the cutoff, but still the problem is that your level may not be achieved. So either you will be little less than the alpha, or you will be little higher than the alpha. So these kind of problems are there, but with this asymptotic test, that kind of problem can be removed. So that's why people often try to use asymptotic test if possible. So is it okay?
Yes, sir.
Okay. So now let us talk about the interval estimation. So in interval estimation, already in the very first lecture you have seen when we have talked about the height weight distribution. So for a given height, the weight, there was a range. Always there was a range. And also we have talked that in regression problem, it is always a challenging part, that not only you give some particular value for a particular known value of y for a particular known value of x, instead of that you need to give an interval such that people can associate with it very properly. Otherwise, only one number will never be satisfied by no one, and it will be misleading. So you need to predict some value, or for a particular number you need to give an interval. So say for example, if your data are coming, we will talk about normal distribution as an example typically. So interval estimation, the concept is this, that you will construct a random interval. That means the lower bound and the upper bound of the interval will be a random variable, or more precisely it will be a statistic. It will be free from any unknown parameter. It will be a function of data only. So that random interval will contain the true value with a certain probability. Remember this thing. A random interval containing the true value with a certain probability. So that means that the true value may not be within that interval. It may be within that interval, it may not be within that interval. So if it is within that interval, that probability should be a pre-decided probability, which people usually write as 1 minus alpha, or sometimes written as 100 into 1 minus alpha % confidence interval. So let us talk about it that in this way, that the confidence interval is a pair of statistic Lx and Ux. Lx stands for the lower bound, Ux stands for the upper bound for a parameter theta, and under true theta, Lx and Ux will contain the true value of theta with probability 1 minus alpha. Alpha you can choose 0.01, 0.05, something like that. So here this is a very nice example that x1, x2, xn are IID random variable with normal mu sigma square, where suppose mu is known, then the 100 into 1 minus alpha % confidence interval of mu is this. So after learning testing, it is a very trivial exercise that you already know that xi's are IID normal mu sigma square. So x bar already you know that follows normal mu sigma square by n. Sigma is known to you, so you know that root n x bar minus mu divided by sigma is following normal 0, 1. As simple as that. You can call it z. So already you know that within this range minus z alpha by 2 to z alpha by 2, within this range, so probability minus z alpha by 2 z to z alpha by 2, this probability is 1 minus alpha. Okay, now you replace the value of z that you know, root n x bar minus mu divided by sigma. Sigma is known, so we are lucky enough z alpha by 2 is 1 minus alpha. Now you need to do the side change in such a way that mu will be in the middle and rest of the thing will go in both of the sides. So it will be x bar minus z alpha by 2 divided by root n, or maybe I can write here sigma by root n, and upper bound is x bar plus z alpha by 2 sigma by root n to 1 minus alpha. So immediately you can see that Lx is x bar z alpha by 2 sigma by root n, and ux is x bar plus z alpha by 2 sigma by root n. Okay. Now please tell me what will be if sigma is unknown? When sigma is unknown, what are the change? What will be Lux and what will be Lx and Ux? What will be Lx and what will be Ux? Tell me. What are the changes you need to do when sigma square unknown?
Sir, we'll consider sigma square as also as a random variable.
So what will be the estimator of sigma square? You need to estimate it. When it is unknown, you need to estimate it. What will be the estimator? What will be the estimator of sigma square when xi's are following normal distribution? More precisely, what will be the unbiased estimator of sigma square?
So that S1 we studied in the last class.
Yes, tell me the expression.
1 by n summation x,
Unbiased estimator I am asking for.
summation xi minus x bar whole square.
This is not unbiased estimator.
1 by n minus 1
by
instead of 1 by n.
Yes. So sigma square hat is this. So if you plug in sigma square hat here, what will be the distribution? So instead of sigma, if you write sigma hat. What will be the distribution of this expression? So root 10 x bar minus mu by sigma hat. What will be the distribution? Is it so new to you? We have done the entire construction in the class.
So it will be T distribution.
Correct? Degree of freedom?
N-1.
N-1. So what will be the lower bound and what will be the upper bound? So do the similar thing. What are the changes you need to do, or it will naturally come for the lower bound and the upper bound? If you have any difficulty, then let me know. Where are you facing difficulty? Or you please give me the answer. What will be the lower bound? This kind of questions will come in exam. Suppose data given, you are asked to calculate the lower bound of a confidence interval or the upper bound of a confidence interval. This kind of questions will come. So please tell me, where is the difficulty to find out the lower bound?
In the previous problem, when we were finding the confidence interval for the mean, in that z alpha by 2 into that sigma by root n, how did that sigma by root n come? Okay.
So from here to here, our goal is to keep mu in the middle and take rest of the thing in the other side.
Okay.
So first I multiply this quantity by sigma, all quantity by sigma. So sigma gone from the middle.
And
then I divide all quantity by root n.
So
Right.
instead of mu in that equation, instead of mu, we can put sigma square, and instead of x bar, we can put sigma cap square, and instead of z alpha by 2, we can put T alpha by 2.
No, here what you want to put? Sigma. So you replace it. Okay, tell me. In place of x bar, what should I put?
Sigma cap square.
Why? I'm
Because
no. When sigma square unknown, I am looking for the confidence interval of mu also, mu only, not sigma square. I am doing the same problem. I am just assume that for mu known, this is sigma square known, this is the thing, and for sigma square unknown, confidence interval of mu.
So then, should it be same? Just z alpha by 2 will be replaced by tau.
Only that.
And I mean that sigma hat will be replaced.
Will be sigma
Yeah.
cap.
I mean
Yes.
sigma will be replaced.
Yes, yes. So this will be tau alpha by 2. Sorry, let me call it sigma hat divided by root n and x bar plus tau alpha by 2 sigma hat root n. Only that much. Yeah. Very simple. Okay, so here you notice one thing, that in both of the cases, the range of the or the length of the interval, how much? How much is the length here?
2z alpha by 2 into sigma by
2z
root n.
alpha by 2 sigma by root n, and here is 2 tau alpha by 2 sigma hat by root n. Now you see that as n goes to infinity, where it will go?
0.
0. And this will also go to 0 as n goes to infinity. Okay. So confidence interval will be always narrower and more narrower if your sample size is increased. So that is a very crucial observation, and that is a very good quality of a confidence interval, that it will be more and more narrow when your sample size increases. That means you, with a very high probability, you will reach or you will engulf the true random variable. So here is an example, a very small sample example. 50 samples are drawn, that means 50 times the iteration is done. Sample size is 8, and they are taken from normal distribution, and the confidence interval is constructed. So here you can see that this true value is 0. Estimated values are these black bubbles, black circles, and the confidence interval is the point from the top to bottom or bottom to top, whatever way you want to consider. This red marked interval doesn't contain the true point of the or the true parameter value, which is 0, but rest of them, they all contain the true parameter value. So here you can see that you have an interval, and this interval are because of this normal distribution or the tree distribution, they are symmetric interval. These interval either containing the true value or not containing the true value. For these red intervals, they are not containing the true values, but the black interval, they all are containing the true values, but they are not in the middle. True values are not in the middle. The middle is the estimated value of mu hat. They are in the middle. So I hope from this diagram it is clear that true parameter value need not be always within the confidence interval, but with a high probability it will be within the confidence interval. Is it okay? It is a probabilistic statement. So is it clear from this diagram? Any query? Okay, so this is what we got so far. This one, okay, so let us see this one. Confidence interval of sigma square, because it is asymmetric case. Any other query do you have regarding estimation testing? So say 95% CI of sigma square, xi's are following IID, normal, mu sigma square. Both are unknown, mu unknown, sigma unknown. So sigma square hat is 1 upon n minus 1 sum over xi minus x bar whole square. Okay, I running from 1 to n. That thing you already know. Then let us start with this expression, that sum over xi minus x bar whole square, I running from 1 to n. This is following sigma square times chi square n minus 1 degrees of freedom, that you know. And that implies sum over xi minus x bar whole square, I running from 1 to n divided by sigma square is following chi square n minus 1 degree. Now you can see that chi square distribution will be looking like this. So if you just consider the upper alpha value, then this quantity, if you say chi square alpha n minus 1, this region is alpha, and this region is also alpha, then what will be the name of this point according to this notation? So I have to take it alpha by 2. Yeah. So what will be the name of this point? So alpha is 0.05 here, because we are looking for 95% confidence interval. If this point is chi square alpha by 2 n minus 1, what will be the name of this point?
Minus chi square alpha
No,
by 2.
no. Chi square
Chi
is
square
always, chi square is always positive. Yes, please tell me. It is square quantity.
So
Chi square
1
minus
1 minus alpha
1
by
minus
2
alpha by 2
n minus. Okay. So what you know from here, that xi minus x bar whole square, I running from 1 to n divided by sigma square. This quantity, it lies between chi square alpha by 2 n minus 1 and chi square 1 minus alpha by 2 n minus 1. This probability is 1 minus alpha. So this region. Within this region, falling, that probability is 1 minus alpha. So again, you have to do the side change in such a way that sigma square will be in the middle, rest of the thing will go both of the side. So you tell me, how will you get it? From this expression, you have to do the side change inversion in such a way that sigma square will be in the middle. You will get the lower bound and the upper bound. This is always the trick for computing confidence interval. You find out the proper distribution and then do this job.
So lower bound will be summation xi minus x bar square by chi square alpha by 2 comma n minus 1.
Xi minus x bar whole square I running from 1 to n divided by chi square alpha by 2 n minus 1 and upper bound.
Numerator will be same. Denominator will be chi square 1 minus alpha by 2 comma n minus
1 chi square 1 minus alpha by 2 n minus 1. So this quantity is Lx, this quantity is. So they are no longer symmetric. Okay. So this quantity and this quantity, they are different. And very easily you can see that this is larger than this. So when you divide the same quantity by this larger number, it will be less. And you divide this same number with the smaller number, it will be more. So this is in the upper bound, this is in the lower bound. Is it clear? This is larger, it is coming in the denominator first. This is less, it is coming in the denominator after that, such that this value will be larger than this. Similar way, if you try to have a confidence interval for the ratio of two variances, as you have done the testing, then also you will get F distribution, and to get the confidence interval, the same trick you have to do. You have to have the ratio. And here will be F alpha by 2 n minus what? Here will be F, n minus 1 m minus 1, F 1 minus alpha by 2 n minus 1 n minus 1. This kind of way. And here you will have sigma 1 square by sigma 2 square, something like that. So this is the trivial job. So I think I have given you the two references from these two books which are usually followed in second year courses, and in this page you will get all the links of different testing problems. Okay. So, and which way cut off, what are the alternative, all these things. There's a very nice page, Wikipedia page. So from here you can refer and you can work on it whenever it is necessary for you. So anything else before we leave and conclude? So from the next class we will jump into regression full-fledged. All the prerequisite we have covered. Any query? Revise it. Don't leave it for the last night. Because question will involve your idea from probability course as well as whatever we have done in this course. You need to have a very strong idea in probability. From next class we will do regression. And the estimation portion of the simple linear regression will be in your quiz. The question is already set and it is already uploaded in the Moodle. Okay. So also try sometime this kind of problems that are given here, because these are the very fundamental problem that one should do while doing estimation and testing. I think nothing much new is there. Important problems, because remember the thing that to find out the MLE you need not differentiate. You just need to find out the maximum. Differentiation need not be the only way. If the function is not differentiable, you need not go for the difference. Out to the maximum. So be careful and read good books and see their examples. I think these two books has given nice examples at the same time. So you can read from that Hogg and Craig or Rice books. Okay, thank you then. Next day we will do the regression. Okay, thank you.